Okay, also let me first thank the organizers for the opportunity to introduce our work. Today I'm going to introduce our work on the electron structure of the nickel 327 phase. I'm Xingjiang Zhou from the Institute of Physics, Chinese Carbon Sciences in Beijing. So let me first thank my colleagues, collaborators. This is group I have in China. And the work I'm going to talk about today is mainly done by 3 students, Jinsheng Wu, Xiangyu Luo, and also Jiangang Yang. Yeah. Also have collaborations with many groups in the laser RP system development. Also we got some single crystal samples from many groups like bismuth 212, 223, potassium iron arsenide. Also, particularly we got single crystal lanthanum 327 samples from Professor Meng Wang's group. And we also have some theoretical theoretical collaborations and discussions with many people like Tao Xiang, like Han Choi, Chen Wama, Xingjiang Wu, and also Dao Yao. So today I'm mainly, after brief introduction, I'm going to mainly talk about the two topics. One is on cuprates. Actually, this topic is really related to the second one, as you can see later on. Then I'm going to talk about our opposite measurements on the lanthanum 327 single crystals. Eventually, I'll give a summary. And in my group, actually, we're using laser as the source for the RPS. I think the main advantage of using laser to do RPS is that it can achieve a very high instrumental resolution. Like we can achieve about 1 milliball in resolution and daily. Okay, and actually, in the last more than 10 years, we have developed 3 systems. Like in the first one is just the laser RPS. The second one is the spin resolved RPS. Third one is just the way you can measure the 2D momentum at the same time. And last year, actually, we developed the FoUS system, so-called the ultra low temperature RPS. In this system, we just can cool some temperature from the usual 10 Kelvin to below 1 Kelvin. We can achieve 0.8 Kelvin at the present. I think that's the lowest temperature so far people can achieve in RPS measurements. Also, we also further just improve the energy resolution from the previous 1 milliball to better than 1 milliball. We can achieve something around 0.4 or 4.5 milliball. We are trying to reach 1 milliball resolution. So because of this development, actually recently we have measured the superconducting gap symmetry in the potassium iron arsenide system. And this actually system is very interesting because it has only hole pockets, not only near gamma points, but also near M point. It has only hole pockets. So it's interesting to see what is the pairing symmetry this system has. But this system has a very low TC. TC only about 3.6 Kelvin, and the gap size is the maximum is only 1 milliball. So that's why it's very difficult to do the measurements. But actually, from our latest ultra low temperature RPS measurement, we can clearly see the foam surface or the band structure. We clearly observed the gap structure, the momentum-dependent gap structure for the 4 foam surface sheets, 3 around the gamma point and 1 around the M point. So eventually, we get the gap structure, and I think our measured gap structure, together with the locations of the nodes, are consistent with the nodal S plus minus gap structure symmetry. So here the gap sign sign from the gamma point to the M point, 1 plus minus. So that's the S plus minus gamma to M, just the symmetry. Okay. So also I say by using this RPS, actually we gain some new insights on the manifold effects in cuprates. And previously people know we have the famous 70 milliball little kink in bismuth sample and other signal samples, but we also have the 40 milliball antinodal kink that is only observed in bismuth 212 in the signal state near the antinodal region. But from our latest measurements, we found that actually, in another direction, in both bismuth 212 and 201, we can see the coupling of electrons with both modes, 70 milliball and 40 milliball, both in bismuth 212 to 201.
Also, near the end of the region, you can also see the electrons coupling with both the 70 millivolt and the 40 millivolt modes. That means the ubiquitous coexisting 70 millivolt and 40 millivolt modes coupling are observed in different materials and are actually at all moment space from the node direction to the node direction and at all temperatures above TC, below TC, and for all dopants. That really, I think that's the new insight we obtained from the laser pass measurements. We are really coexisting 70 millivolt and 40 millivolt electron coupling coexisting in all the materials at all temperatures and at all moment space. So then I come to the first topic is about the just the origin of RTC superconductivity in tri-layer cuprates. As you all know, that actually in cuprate superconductors, the TC depends sensitively on the number of covalent planes in the structure unit. Okay, and usually the number three layers has the maximum TC. So as you can see from here, that it holds both for the bismuth system, sodium system, and the mercury system. 3 is the best for the highest TC. And also, actually, as you already know, usually TC depends sensitively on the doping. It goes up first, then goes down again. It forms a dome-shaped and phase diagram. But in 3-layer systems, it's different. Like in bismuth 223, you can see that TC goes up first with increasing doping, reaches the maximum at the optimum doping, but it keeps almost constant in the orbital region. So what's why this phase diagram, of course, is different from the usual phase diagram we can see. So why this? Okay. So then we performed laser tests on this bismuth 223 system, and before that we have a new sample, and of course in bismuth 223, in one structure unit you have the 3 covalent planes. We call the central one inner covalent plane, 2 outer ones to outer plane, so OP and IP. That's what I'm going to use in the later on talk. And also for this bismuth 223 sample, and we anneal the sample and a very high oxygen pressure of 170 atmospheres to just make it heavily overdosed. So, but TC is still high. It's about 108 Kelvin. It's very high TC, but it's heavily overdosed. So then we measure the Fermi surface of this bismuth 223, and you can see from the Fermi surface, from constant energy contour at different binding energies, we can identify clearly 3 Fermi surface sheets. We call it alpha, beta, and gamma. Okay, so this is the first time that people observe 3 Fermi surface sheets in bismuth 223. I think it mainly because it's heavily overdosed. And in this case, the gamma Fermi surface has a doping level about 80%. And the alpha and the beta, alpha is the heavily overdosed, so it's 0.37, beta 0.22, and gamma is 0.08. So these two are heavily overdosed, but the gamma Fermi surface is heavily underdosed. So we have 3 Fermi surface sheets observed. Also, we measured different gap along the 3 Fermi surface sheets. Okay, we have alpha and beta and gamma, and we can see that the gamma Fermi surface has the largest sibling gap. It reaches about 60 millivolt. But the alpha and the beta Fermi surface has a smaller gap. It's around 20 to 30 millivolt. So we have different Fermi surface gap size along different Fermi surface sheets. Okay, but gamma has the largest gap. So for this 3-layer system, actually we can use a 3-layer interaction model to describe all the observed properties. So we use this in this model. We consider the intralayer Hopkins and also interlayer Hopkins. So interlayer Hopkins will have T prime, double prime. Interlayer Hopkins contains 2 sides, the 2 aspects. One is the inner one, inner to outer. The other one is the outer to outer. We have TIO and TOO. We also consider the interlayer pairing. Okay, in the same state. Also interlayer pairing. So a pairing interlayer, also intralayer. So by using all these parameters, one set of parameters, actually we can describe all the observed phenomena, like Fermi surface,
like all the band structure evolution with the momentum, like even the observed just the probability of band habitation, also shifting gap. So just one set of parameters, and by using this three-layer model, we can describe all the observed phenomena. I think from this simulation, actually, we can see that first we see there's a strong just the inner layer in hopping, particularly outer to outer TOO. That's very important. That causes the pilot splitting of the alpha and beta band. So actually, the gamma band is derived from the inner coordinate plane. Alpha and beta frame surface come from the outer two coordinate plane. Because of the interaction between the two, in hopping between the two, there's something like the pilot splitting. So the splits between alpha and beta frame surface. So we have gamma frame surface from the inner and alpha beta frame surface from outer coordinate planes. So then I think to understand why the TC is high in this episode 223, I think we need to understand that usually superconductivity is realized by going through two steps. The first step is to form the co-pairing. The second step is that the co-pairs just form coherent states. So the pairing process and the phase coherent process usually in conventional superconductors they may occur at the same temperature, but in some unconventional superconductors they may happen at different temperatures. They may have the pairing first and also the phase coherence the second. So they may happen at different temperatures. So this is an idea proposed by Emery and Gibbon long time ago. And also, usually for many materials, the pairing and the coherence may occur in only one thing, one entity. But then there's one idea that's a so-called complete picture. That is, whether it's possible to optimize the pairing and phase coherence in the two different things. Like if we have two layers, well, one layer is heavily underdoped, but then it has some larger sibling gap. That means it has some higher pairing strength. This is responsible for higher pairing strength. The other layer is heavily overdoped. That means it has some high phase stiffness. It has some higher just coherence temperature. Then we just put them two together, and if there's some interaction between them, and then we can realize higher TC. So this is a so-called composite picture proposed by Steve Gibbon and just some years ago. I think our results on PISM 223 are very consistent with this composite picture. That means because in the real space, we have three obtuse planes. The inner plane has a doping only 80%. The other two planes, each one has a doping about 30%. It's heavily overdoped, heavily underdoped. For each of them, if you just have each of them, they don't superconduct at all. Like 30%, they don't superconduct. 8% heavily underdoped. It needs a border of superconducting, becoming superconducting, but TC must be very low. But if you put them together, there's some interaction between them. Actually, TC is very high. It's 108 Kelvin. So I think this is consistent with the composite picture proposed by Gibbon. Okay, and also this picture actually can also explain why TC does not change much in the orbital region. Because if we compare the open doped PISM 223 and heavily overdoped 223, mainly the average doping level goes from 0.18 in open dopes. TC is 110 Kelvin. For our heavily overdoped sample, the average doping is 0.22, but TC is 1.8 Kelvin. So if we look at the alpha state, actually we have three frame surface in open doped sample and overdoped sample. Alpha, the extra co-doping actually goes to the alpha frame surface. But beta and gamma, these two frame surface sheets does not change much. The doping level does not change much.
Also, the gap does not change much for the beta and gamma. Only the alpha changes much more obviously in this with doping. So that because as we know from in the composite picture, just the gamma Fermi surface is responsible for the pairing strength, and the beta Fermi surface is responsible for the coherence. But these two Fermi surface sheets does not change much with doping, and that's why the TC does not change much in the observed sample. So I think that's by using the just the composite picture, we can also understand why TC does not change much in the observed sample. So this is basically is the work we have done in the bismuth 223 sample. Then I come to the second topic on my talk. That means that is we observed orbit-dependent electron correlation in lanthanum 327 sample, and as we already heard in the previous days, and also in just in the year last year, and Professor Wangman's group discovered the superconductivity TC is about 8 Kelvin in the lanthanum 327 sample and high pressure. So this 327 actually it consists of two nickel oxygen planes, but in the middle they have some oxygens connect these two octahedrons. So TC is 8 Kelvin, and determined from the resistivity, also the magnetic measurement, and also from the structural analysis, it shows that at ambient pressure there is some angle between these two, between the nickel oxygen nickel and about change. Okay, at ambient pressure is about 168 degree, but at high pressure it becomes straight. It becomes 180 Kelvin, 80 degree. Okay, this is phase diagram they observed. So then, of course, it's very important to understand the electron structure and in order to understand the origin of the superconductivity. And band structure calculations indicated that actually near the Fermi level, the electron states are mainly come from the in-plane nickel ds square minus y square orbital, and also outer plane just dz square orbital. So this in-plane ds square minus square orbital, and outer plane dz orbitals connected by oxygen. Okay, so these are the basic just the electron structure from the lanthanum 327, and also there's some training here. Then we got a sample from Professor Wang's group, and we performed RPAS. We performed RPAS both in the synchrotron-based system, Shanghai synchrotron radiation facility, and by using photon energy 75 eV, we can map the larger London space. Okay. Also, in our lab, we use laser to gather the Fermi surface. Okay, this is the Fermi surface obtained from laser. And basically, because in lanthanum 327 system, there's some lattice distortion. That means there's some octahedral rotation. So that's why actually there's something like a root 2 by root 2 structural distortion. That's why we can observe two sets of Fermi surface. Okay, actually there are another Fermi surface sheets. Those are just folded Fermi surface from the distortion. Okay, so there are two sets of Fermi surface observed due to lattice distortion. So the main Fermi surface structure consists of mainly two Fermi surface sheets. One is called alpha. This is the central one, is like a circle. Okay, this is one alpha, and they correspond to is an electron-like, and they correspond to doping level about 0.2 electron per nickel. So this is the alpha Fermi surface, and the second one is the beta Fermi surface. This is red one. It's a hole-like. If you just by counting the Fermi surface area, it's corresponding to doping level about 1.25 hole per nickel. So we have mainly two Fermi surface sheets observed in 327 at ambient pressure. So this is the Fermi surface obtained from band structure calculation. I think these two are consistent with each other. Okay. Then we also measured the band structure along some high symmetry cuts here. Okay, mainly in this case we can really see the alpha band, okay, beta band along the diagonal direction is to adjust the degenerates, okay. But I think also alpha band, also particularly near the pi points, we see a very flat band. This band is about 15 millivolt below the Fermi level. And you can see also there's some EDC peak here. So this is the flat band near the pi points. That is 50 millivolt below the Fermi level. So this is a prominent feature we observed in Lensdom 327 system. Also, to determine the orbital character, we performed some polarization dependent RPS measurements. We just use different polarization, like the E vector in this way, the E vector goes this way, and also some perpendicular E vector components. And in this case, we have E vector goes this way. So we map the Fermi surface, and also we get the different band structure and a different polarization geometry. So by analyzing the whether some and particular E vector, whether some orbitals are allowed or forbidden, we can determine just the orbital character of this observed Fermi surface heats. I think I shall say the conclusion based mainly for alpha Fermi surface, beta Fermi surface, and they are consistent with the dx square minus y square orbitals. Okay, and for the electron states near the pi points, and mainly that's the gamma band. That's consistent with the dz squared orbital. So from the polarized light measurements, we can determine the orbital characters of the observed bands. Actually, we also performed some band structure calculations, and from the band structure calculation, we found that if you don't put u into the calculation, mainly the dz squared band, just that's mainly in this case actually crosses Fermi level. Okay, but if you put some u, like in this case we put a u equals to 3.5 eV, this band that goes below the Fermi level. So by putting some u, we can move the position of this so-called flat this squared derived flat bands from above the Fermi level to below Fermi level. And actually, in our case, from our experiments, we found that actually this band is below Fermi level. So we have to put some u in order to understand this behavior. So then eventually also I want to compare our results of 3 to 7 with that of 4 to 310. And this is the result just Professor Danta South group obtained in the system 4-3-10, and this is the Fermi surface measurement Fermi surface mapping. This is obtained Fermi surface because this is central one. This is another one. Also, the third one is the gamma Fermi surface. And in the 4-3-10 case, actually in this region, there is a flat band that crosses the Fermi level. That's why that gives rise to this gamma Fermi surface here. Then when it comes to 3 to 7 system, as we measured here, this is matter Fermi mapping. This obtained Fermi surface. We have the alpha Fermi surface, beta Fermi surface, but here we don't see gamma Fermi surface because in this case, gamma band is 50 millivolt below Fermi level. So if you compare 3 to 7 system to 4-3-10 system, mainly the band structures look similar, alpha, beta, and gamma, but the major difference, quantitative difference, lies in the gamma band. In 4-3-10, gamma band crosses Fermi level, but in 3 to 7, it's below Fermi level. I think that's the main difference. Okay, and eventually, and also we also measured the orbital-dependent band renormalization in 3 to 7 system. We have alpha band. Mainly we have alpha bands, beta bands, also the gamma bands. We measure the band renormalization either along the axis or along the diagonal direction. So we have, in this case, we have measured the alpha band along the axis, and with this is band calculated the band, and this is something like a 1.8 renormalization factor if we want to make them match each other. Also, this is the along diagonal alpha beta bands calculated one, and this method one. This is the beta bands method one, calculated band one. This is about 2.6 renormalization factor. And for the gamma bands, the calculated one without u equals 0, it crosses the Fermi level. It has this kind of this large and just bandwidth, but the measured bandwidth is much smaller. Okay, so this is along the diagonal. This is along the axis. So the measured bandwidth is much smaller. So it's about from 5 to 7 times renormalization. So by putting them together, we found that actually in the dx square minus y square derived bands have something smaller band renormalization, like between 2 or 3 in this case. But the dz squared derived bands just show much larger just renormalization factor here is between 5 to 7. So this is around 6. So it's much larger in this case. Okay. So eventually, just I give a summary to my talk. And we found that in 3-layer couplets, actually, because we have some inner layer and outer layers, actually, we found that actually the sequentivity can be well described by using some composite picture. In this case, just the inner one has much smaller doping level, has a much larger pairing large gap. That means it has a much larger pairing strength. But outer one heavily doped, but it has some very large just coherence temperature. So by putting them together, you can form some the superconductor with DC much higher. Is in this case around 110 Kelvin. Okay, so this idea can actually can be borrowed, or actually has already been borrowed, to understand just superconductivity in the liquid samples 3 to 7. Because in this case we have two kinds of bands. One is from the dx square minus y square. The other one is from dz square. So some people propose that maybe dz square has strong correlation, correlation, also has very much stronger parent strength. But dx square minus square just can be act as the high just coherence temperature. By this putting the two together, there's some competition interaction between them. They may also just give rise to some high TC in this case. So I think from our results and particularly just our electron structure measurements on 3 to 7, we provide some important information to understand electron structure of this system and also try to understand the superconductivity origin in the system. Okay, with that, I thank you for your attention.
Thanks a lot, Xingjiang. Again, this is related to FoUS question, and look at these. I mean, you see like strong Fermi surfaces, and then you wonder, where's a density wave gap? Because you saw from Liling's result, it looks like a large part of the Fermi surface is removed at the density wave transition. We had a similar puzzle when we were looking at Dan's original data on the 4310, that they really weren't seeing much evidence of the density wave gap in the ARPAs. Do you have any feeling for that on the 327?
Actually, you're right. Actually, we observed some gaps around the Fermi surface, and we are still measuring. Yeah, it's not completed yet. We see some gaps around the Fermi surface. Yeah, here. But still we are measuring. It's not finished yet.
Okay,
yes.
Great. Thank you.
Yes. Yeah.
Any more questions? Jimmy.
Yeah, so thanks, Xingjiang. That was beautiful data. So just follow up on Mike's question. It's a dumb question, but can you do the measurement above the ordering temperature?
Actually, we did, yeah. We did some temperature measurement, temperature-dependent measurements for the system. But at present, we only have one cut along this direction, yeah.
Mm-hmm.
Basically, we don't see much change above 150 Kelvin.
so far.
So like the Z square still is below the Fermi.
Yeah, it's still
value.
still about the 15 millivolt below Fermi level.
Okay, thank you.
Yeah. So that's yeah, we measured that. Yes.
All right. Very, very interesting. Really, very interesting data. Interesting to hear what you find with your latest story that you were just talking to us about. But thanks very much for the